Okay, everybody, this is September 3rd, 2025, ESM 105 class. It's good to be back in the classroom, and I wanted to point out to everybody that I'm recording, I'm recording these lectures here, right? They don't have the screen on the board, but hopefully it's a helpful thing. The recorded lectures are all gonna be linked here on the home page. You hit this little recorded lectures button. It takes you to the playlist I've got where I'll be uploading lectures as quickly as possible, as close to the day that I give the lecture as possible. It's usually the next day because of issues with how the phone uploads to the cloud, the whole thing. Anyway, there's that information that I wanted to get out. Otherwise, I wanted to check in real quick, okay? You should be reading Sand County Almanac. You should be participating in those Friday discussions. And in week 3, you'll have quiz 1, okay? First quiz. If you click the quiz, it's got a description of what the quiz covers. It's going to be entirely on weeks 1 through 2 material, as well as a Sand County Almanac. 13 multiple choice questions, and 1 short answer question relating to the reading. Cool? Sound good? Okay, and I give you all the stuff here. Like, hey, you can reference your PowerPoint as well as the reading, but the time limit's 60 minutes, so if you're looking up every single answer, you'll run out of time. Okay, good. Please only use course material in answering these questions. The goal of these quizzes is to get you to engage with the course material, okay? All the information you need is in those PowerPoints that I'm given and that I've uploaded for you. So honestly, it's probably more trustworthy to use that than searching questions or plugging them in or whatever you want to do. This is honestly probably the easiest solution if you need to look anything up. Any questions about that, please?
Is the quiz 3 given under the impression that we're already finished with the Sand County Almanac?
It is, yes. So that's one of the things that the department really didn't want me to. I got a lot of free reign when I took on this course this semester. And one of the things they really wanted was to have you still read these books at this pace. So I did eliminate 1 reading because I've read these books and I'm like, this one's a little redundant with stuff. Bringing it to the table was an assigned reading, so I pulled that one out. And now it's 4 books, okay? But it is a lot. It's a high pace throughout the course. Though, a Sand County Almanac's the longest one. And I'm okay if you breeze through some of the, say, like diary sections where they're literally just logging, sunrise was at this time, and then I saw these birds, and I saw this, It can be soothing, or it can be frustrating, depending on where you're at when you're reading it, The other books, some of them are very quick reads. Stuff is that's a day, maybe 2. And Cradle to Cradle is really fast as well because it's printed on special materials. It's part of their whole story of the book, so it's really short. The pages are thick. And there's a reason nobody ever printed on that again. Yeah?
So for all the short answer questions on the quizzes, they're all going to be about the readings usually, right?
Yeah, that's gonna, usually it's gonna be multiple choice questions relating to the lecture and then short answer questions relating to the reading. Because I don't want to have a question like, what was the answer? It's hard to write a multiple choice about a reading that's really about how much did you understand, what did you take from it? The short answer questions are usually like, what did you take from this book? What did you take from the reading? Give me enough information to convince me that you read it. Yeah. Awesome. Additional questions, scanning the room. Yes?
And in those short answer questions, will we use quotes or anything from the book?
You can totally use quotes from the book. Yeah, you can put it's really a couple of paragraphs and you try to convince me that you read the book. So if you throw a quote in there, the biggest takeaway I had was this concept here. Sometimes there'll be a question about a specific concept, like the new land ethic. And you'll be like, oh, the new land ethic. I think that had to do with this. Let me find it in the book. Oh, this quote from the Sand County Almanac perfectly illustrates the new land ethic. Quote, what I took from it was this explanation. Awesome? I love it. Okay, additional, I'm scanning the room. I'm scanning. Okay, very cool. Let's go ahead and pop open the PowerPoint again. Weeks 1 through 2 material. So the previous lecture, I went through I was honestly kind of bummed. Had to skip some stuff that I was excited to talk about with you in person. But we got through the history section, really. We got through sustainable development, environmental ethics. We got through a little TEK talk. We got through into the basic principles of science. And I went through this slide and talked to you about deductive versus inductive reasoning. And I think this is a fine place to pick it back up. There might be a slight overlap between the recorded lecture and what I talk about. But hey, let's be honest, I can see the views on that YouTube video. Not everybody saw that anyway, so we'll talk about it right here. Okay? So when you might ask in this natural resource conservation class, why are we starting with so much just scientific method, experimental design, interpreting statistics talk? And I know that I've laid this out for you once before, but I really think that it's super justified and something that, everybody should care about. You need to understand what a good experiment looks like because people want to determine if conservation efforts have worked in the past. If a conservation effort has been implemented, you need to have clear deliverables of what can we measure to show that it worked, especially if it cost a bunch of money from limited funds. If they're saying we have enough money for 5 conservation projects, different groups have proposed 30 of them. Which ones are we going to choose? It would be great if you could look at studies about the previous times these conservation efforts have been used. Like, oh, they did this 10 years ago, and it didn't work. Or they did this 10 years ago, and it did work. Primary literature articles can sometimes look like they show positive results, but it's not of the magnitude that is actually useful when you're trying to prioritize conservation efforts. So knowing how to understand experimental design, reasoning, and how to understand statistical outputs is really important. It'll only be through this week, and then next 2 weeks are all ecology background, which will really flesh that out about what sort of models ecologists use. Okay, different types of reasoning. 2 broad categories of reasoning are deductive and inductive reasoning. People usually know about deductive reasoning, or at least they know about Sherlock Holmes, and they say, oh, it's simple deduction, What is deduction? What is deductive reasoning? It's when you take a broad accepted statement, like a truth, and then you stack that with some other truths, and you apply them all to your answer. You've got a question, and you have proposed an answer. And if all of these statements that you're accepting as true are validated by that, you're like, oh, I have deduced that this is the correct answer. People will tie it to Occam's razor and all these things about, oh, the most simple answer is probably true. But in its actual definition, deductive reasoning in the scientific method is really saying, I'm going to have all these theories, and I'm going to have all these accepted rules about how the world works, and I'm going to try to answer a question by making it fit into those rules. So that's deductive reasoning. Whereas inductive reasoning generates those rules. You take a lot of individual observations. On the video, I just used gravity because it's, straightforward. It's like, oh, I dropped this, okay, it fell to the ground. Oh, it did it again, it did it again, it did it again. I dropped something else, something heavier, something lighter, different heights, different environments. And over and over and over and over and over again, I've got all of these individual individual examples, and I am going to use inductive reasoning to build up a rule that things fall down if nothing's in the way, okay? Then you can take the rules that you developed from inductive reasoning and use them for deductive reasoning. How'd that thing get on the ground? It probably fell off the table. I used the cat example in my online lecture. Anyway, inductive versus deductive reasoning. It's nice to use the terms correctly because you'll be surprised how much you can use them in your day-to-day life. Excuse me. It's hot. All right. Hypotheses. Now, I had to record 2 lectures that were both on hypothesis generation on Friday for this in another class. And so I'm a little bit fuzzy, but to somebody who watched the video, can you help me out? Can you remind me, did I give the hypothesis example? Did I do the radio thing? I talked about the radio? Okay, great. That's going to save us a lot of time. That radio example takes a lot of time. Formulating hypotheses with this if blank and blank then blank format will be helpful. I know I wrote it on the board once in this class already. Gosh, at least I think it was in this class. I'm teaching too many classes, but that's not your problem. All right? So if you want a refresher on the if blank and blank then blank for when you're generating hypotheses, I will do it again. It's really helpful. Would that be helpful for people here, for anybody here? No, we want a refresher on that? Are you comfortable with it? I see some gentle nods. Let's just do it real quick. Okay? I get to write on the board. That's engagement, you know? If blank and blank then blank. Okay? So I'm going to blank projector. I'll leave it up. It's fine. You can read it then. Good. Okay. So I've got a hypothesis. Let's just generate a hypothesis. Salinity of soil water affects plant growth rates. Cool? I'm just going to say soil salinity affects plant growth. It's a very general hypothesis that needs a lot of revision, right? I'm saying one thing, okay, affects something else. I am saying an independent variable affects a dependent variable. So when you're laying it out as an if blank and blank then statement, okay, you go if hypothesis. All right? So if soil salinity affects plant growth and experiment, I irrigate seeds with solutions of different salinity and measure plant height. You can get more detailed on this if you want. And measure plant height after a month. Okay, then expected results if hypothesis is true. Okay? So, if you get comfortable laying things out in this way, it's really nice for your experimental design because anybody reading this knows what you expect, all right? They know what experiment you're going to do, and they know which results would support your hypothesis. And a lot of times when people formulate hypotheses, they don't do all this. And so you're left with like, but how are you going to test it? So if you always write them like this, no one ever has to ask you that question. Cool. How do we feel about that concept there? I got a thumbs up. I got a thumbs up. Awesome. Projector video unblank. Board down. Screen down. Okay. So, you need to also know what a null hypothesis is. A null hypothesis, it'll come up a lot, okay? Null hypothesis is just that your independent variable does not impact your dependent variable. In this experiment right here, we are saying that salinity impacts plant growth. So salinity is your independent variable, and you're saying that plant growth depends on salinity, making plant growth the dependent variable. If you can get the independent and dependent variables organized really well in your mind, it's going to make everything moving forward easier with experimental design, all right? And if you're designing an experiment, you should know the thing that you think is going to have an impact and the thing that you are going to measure to quantify that impact. That's the independent and the dependent variable. Any questions about that? And then one of the things that you've probably had in a course, maybe in high school, that people love to do it's just a theory thing, you know, and they'll say, oh, you shouldn't say it's just a theory, because a theory is a hypothesis that has withstood many rounds of testing and has not been disproved. So a theory in science carries a lot of weight. And a theory that has lasted so long that it's used for the development of other theories is sometimes called a law, all right? Very good stuff. So saying, oh, it's the theory of gravity instead of the law of gravity is okay. You see what I mean? Cool. Probabilities, okay? I teach a number of upper division courses. Students, I always have to teach basic probability math. You'd be shocked at how many classes this is relevant to. As we're doing it, it's going to feel like, why are we doing all this math in ESM 105? But then when you hit an upper division, you hit ESM 230, ESM 303, one of those things, you're going to be like, oh, I already kind of know this, and it will seem less intimidating. At least this is my goal in presenting probability math to you right now. So, probabilities. Probabilities let us predict how likely something is to happen, which is huge. It's one of the greatest benefits of using the scientific method. It's one of the greatest aims of any ecologist or environmental scientist, right, is to predict what will happen in the future. And you give it a probability, because then if you're wrong, you can say, oh, that must have been the 15% chance of that not happening. That's not really why you give it a probability, right? But probability lets us make a more informed decision on, well, there's a 50-50 chance the bad thing's going to happen, I might risk it. Or there's a 90% chance the bad thing's going to happen, I might not go down that path. You're familiar with the ideas of probabilities, but let's talk about their math. Let's talk about how we can determine them and how you can make more accurate predictions in your own life. And you know, the best thing about understanding basic probability math is you can recognize how unlikely things are around you. And when you see something happen that had like a 0.0025% chance of occurring, it's kind of exciting. You're like, oh, that's a really low number. Maybe my scale for what's exciting has adjusted. You know, ooh, someone's out there. Oh, hello. The door lock on you?
No.
Oh, okay. Oh, gotcha. All right, yeah, that one works. That door works. That door doesn't work. All right. Delicious. So, I'm just really excited about probability math. I was doing recreational reading in the summer, and I was like, I should read Edgar Allan Poe. It'd be so cool. I got bored pretty quickly. No offense if you love Edgar Allan Poe, but it was really cool to come across this quote in one of, I forget what the story was, but Edgar Allan Poe pointing out, oh, look, you know, coincidences. If you don't understand probabilities, you see coincidences everywhere. But if you understand probabilities, you're like, you know, there was a chance of it occurring. 25% is not that low, and it just happened. Just happens sometimes. And with a bunch of big events, anyways, if there's a lot of iterations of an event, it becomes more and more likely. Let's go ahead and take a look here. Oh yeah, my clicker is not working. Boom. Okay, I put in, man, I wish I had moved this slide. These are fresh PowerPoints, so I make adjustments sometimes. Distributions, these fit into the, not really into the probability discussion. So I'm going to come back to normal distribution in just a minute and talk about it, because I don't want to lose our probability basics streak right here. There's a lot of text here because I want this to essentially serve as a probabilities study guide document that you can have for the rest of your life to understand the laws, the basic rules of probability. All right? Basic probability is going to all be here. It's relevant math, I promise. So I've got a nice example here that I made up on the fly to try to talk about. What's the probability of getting a dam? What's the probability of a dam bursting? All right? So you can determine the probability of something happening usually based on previous observations. All right? That's oftentimes how you do it. But sometimes you need to know how likely multiple events are, how likely it is that multiple events are going to occur at the same time. And you need to know how likely it is that an event that could occur in multiple different ways could happen. Very vague, but we're going to talk about each rule independently, and hopefully it works. So right here, you've got some data. It allows you to predict the likelihood of heavy rainfall events, high humidity, and earthquakes in the next 10 years. Okay? Now you have these models that you've generated to predict that. We'll talk about models later. There's a dam. It's only at risk of bursting given a water pressure, a failing turbine, and an earthquake of sufficient power. Okay? So you've got data about these variables right here. So the first rule that we're going to look at is the product rule. What's the probability of this and this and this and this all happening at the same time? You need a perfect storm of events to get the outcome that you're concerned about, which in this case is the dam bursting. So here we are in our example. 5% chance of a turbine locking up. And I did make a slight issue because I edited this a little bit. This references humidity, but it's not relevant to this slide. My apologies. The actual situation is here. A dam which will only burst if there's a specific water pressure, so a rain event, a failing turbine, and an earthquake of sufficient power. So now let's look at some probabilities. Every day, there is a chance, okay, a 5% chance of a turbine locking up. It's an old dam. In July, there's a 15% chance of sufficiently high rainfall to put strain on the dam. In the other months, there's never enough rain to make there be a strain on the dam, so you're only concerned now about July. Fair enough? Because the probability of everything necessary for the dam to fail in the other months is 0, because the probability of a sufficient rainfall event is 0. This is, of course, a simplified example, okay? Every day in July, there's a 0.05% chance of an earthquake occurring based on geologic data. So you have historical records of the earthquakes. But if all three of these things happen, the dam fails and it's a catastrophe. So you're tasked with, well, I got to figure out, this dam is out of date. We need to justify removing the dam. Is this how we justify it? By determining the probability of the dam failing each day? Okay? You run the math, the basic probability math, and you determine, well, there's only a 0.000375% chance of a dam failure each day. It's not a super persuasive number. And somebody who's trying to move that money someplace else, or just not have the dam removed, or not do their due diligence in repairing the dam, might generate this same number and go out to the community and say, you're comfortable with this, right? Look at this probability. It's so low. It's not going to happen. And you only have to worry about it in 1 month. It's because they're using pure probability math. Let's look at how the probability math works with an example on the board. Move the projector screen up a little bit. There we go. So probabilities are usually presented, or I'm going to say that the best way to present probabilities is as decimals. Okay? You can say something has a 1 in 5 chance of occurring, all right? But that's equivalent to a 0.2% probability, okay? So probabilities are decimals. I've actually got that on the projector, so I'm not going to worry about it. If you have your probabilities all as decimals, life is easy. Oh, let me do it like this. 1 out of 5 is equivalent to a 20% chance, is equivalent to a probability of 0.2. How do we feel about these conversions? Okay, that's awesome. That's awesome. So if we've got multiple probabilities, we've got each day there's a 5% chance of a turbine locking up. Well, then if we want to mathematically solve, we should just start with 0.05. That's a 5% chance. And sufficiently high rainfall, 0.15, okay? And an earthquake, which is 0.005, 0.0005. That was the tricky part right there, okay? And you multiply these all together, you get the probability of all the events occurring together. So this symbol right here, the multiplication symbol, is and, all right? So the probability of turbine lockup and heavy rain and earthquake can be determined as such. Okay? The next one's going to be the OR rule. It'll be a little bit trickier. It's not trickier. You just need to know both of them. So I put this right here. I'm saying, like, look at that. People are going to say that's a really low chance. They might use it to shut down a conservation effort. If you can look at how they generated, what they determined the necessary conditions to be, there might be some real dishonesty there. It's very tempting to look at the numbers when somebody does an assessment or produces a primary literature article and not really pay much attention to the modeling or the math they used, because it's dull. So anyways, basic probabilities, okay? You could also make a prediction of how probability of a dam failure is going to change in the future based on, hey, look, it's going to lock up more next year. So we can just adjust the turbine lockup value, okay? And say in 10 years, the probability is going to go up because we're going to change the probability of a turbine lockup. Yes?
This is the chance of all of the scenarios occurring. Is there a way to use the same data to determine the likelihood of a dam breakage under these circumstances?
That would be the likelihood of the dam breakage under these circumstances. Yes, that would be probably an engineering question for them. The idea here is that we've already established that there's a 100% chance that if these things happen, the dam will fail. But it's a really good point because there's probably another situation that leads to a 50% chance of dam failure, right? So you'd add more models to it, essentially, and you adjust it. But the basic probabilities are here.
0.0000375% chance of it 100% happening.
Exactly. Yeah. Really, what this is saying is there's a 0.0000375% chance of these three things happening at once. Okay? But we've proposed that that's the only situation where the dam will fail. And that's exactly how somebody could mislead or use this sort of math to shut down a conservation effort. They say, you told us the dam will fail if these things happen. That's what you said. So we determined the probability of those things actually happening, and it's very low. See what I mean? So this way you can kind of cut them off at the pass and be like, well, we know that they're going to try to use this against us later. Let's not maybe use that language. We'll say this would be, you try to present more situations that would lead to the dam failure. If your goal is to get the dam replaced. Awesome. Product rule. The and rule. We did it. We're good. Now we move into the sum rule. Okay? sometimes an event can happen in multiple different ways. So if we've got here, this example here, now there are two different events that can lead to the same outcome. If there are ever two different events leading to the same outcome, you add the probabilities of each event together in your equations, okay? That'll mean more in this example probably. So there's a giant fish in the dam, in the reservoir behind the dam. And each day there's a 20% chance of it attacking the dam, okay? Effectively, same impact as the earthquake. So we're gonna add this. We've got the probability of turbine lockup, the probability of heavy rain, and the probability of a quake or fish. Because either one is going to have the same impact on the system, right? Or on the situation. We'll get into systems later too. So if the fish probability is 20%, fish is 0.2. And if there's an event that can occur in two different ways, right? You determine the probability of each way the event can occur, and you add them together, okay? So what's the probability of quake or fish? Well, it's 0.0005 plus 0.2. So then I can just modify the equation a little bit and say I'm asking for the probability of turbine lockup and heavy rain and quake or fish in parentheses. And that's going to change my probability clearly, right? Now let's go. Sometimes I like to do this kind of in reverse, where I go more advanced practice problem down to the simplest practice problem. Whenever you're teaching probabilities, you use coins, okay? You flip a coin, it's a 50-50 chance, heads or tails. Yeah, it could land on its edge. We don't factor that in, all right? So we flip it up, 50-50. What's the probability of heads, 1 out of 2 outcomes, or 0.5? Probability of tails, 0.5. What's the probability of flipping it twice and getting heads and heads? Or flipping 2 coins and getting heads and heads? 0.5 times 0.5, 0.25. What's the probability of flipping it and getting heads or tails? 0.5 plus 0.5, 1. Hopefully at some point, I don't know, why do I say hopefully? Maybe you encountered this before. That'd be awesome. But probability math isn't always really appreciated, in my opinion. Trust me, it will come up again at some point. You'll have to understand probabilities, and if you know these basic rules, it'll make your life easier, I believe. Okay. There's a probability of the dam failure. It's written in this example on the slide. I wrote it all as percentages, 5 per 100. Percent just means per 100. So a 5% is 5 per 100. 15% is 15 per 100. Okay? So there we go, boom, or this is the math there and the other way, and now you got a 0.15% chance of a dam failure each day. And if I wanted to know the probability of a dam failure in the month, I could say, what's the probability of the dam failing on July 1st, or July 2nd, or July 3rd, or July 4th, or July 5th? I just add them all together, and that gives me the probability of having a dam failure in the month. You see? And that's very basic and doesn't use any modeling. That's purely probability math. Question?
Are we going to go for conditional probability?
No, you'll be just fine. Yeah. I just want to make sure we got these rules all laid out. Okay, solid? Man, I got too into that. I took too much time, but that's okay. We'll get there. Statistics. Ready? I have taught a lot of courses where we need to do statistics. I will tell you a brief story of myself being an undergraduate, and I was always convinced that I could never go to grad school and I could never be a scientist because I didn't understand statistics and I just wasn't getting it no matter how many statistics courses I took. Now on my end, I wasn't really like trying to read statistics books or looking for any simplified guides online because I was so intimidated by the field. So when I got to graduate school, I had to learn basic statistics, and it took like a couple weeks, and I was like, this is all this was? Is that all there is? You know? And yeah, so my goal now in basically all of my science classes that I teach, which is all the classes I teach, okay, is to get my students caught up to the point where you can go into graduate school if you want and know the statistics that you need to know. So in a day, I'm going to get you caught up to what it took me 6 years and a PhD to get with statistics. And it's shockingly simple, okay? Cool. Statistics, if you remember one thing from your statistics course, it's probably the p-value right here. Folks, remember the p-value, right? And the critical p-value, it's like, oh, the p-value needs to be less than 0.05, right? That's usually what I get when I ask, like, what do we remember about the p-value? It needs to be less than 0.05. But why? And what does that mean when it's less than 0.05? So it all comes back to your null hypotheses, all right? And the p-value is just, look at it, this decimal. That looks like a probability to me. That's what it is. It's just a probability value. It's saying that there's less than a 5% chance of something. I'll tell you what it is. Okay. So a lot of statistical tests are just trying to determine, hey, we observed this data. Is that because there's an interaction between the independent and dependent variables, or was it just due to chance? And it's all these equations that are built around average values and noise in the sample set and all this stuff, all these complex equations. And at the end of all of it, it spits out a p-value. And the p-value, there's a few ways to consider it. One is the probability that you received the results you did just due to chance. So if there's a 5% chance that you received the results that you did just due to chance, that's pretty good. There's a 95% chance that your hypothesis is supported here. 95% chance, pretty good. That's all the p-value is representing. Or the p-value can more specifically say the probability of receiving the results that we did if our null hypothesis is true. So if there's no interaction between the independent and dependent variables, how likely is it that we would receive the results we did? If it's a small probability, then we reject the null. If it's a large probability, then we fail to reject the null hypothesis. Remember that language from your statistics course if you had to take one? Yeah. Okay. So different tests set different significant p-values. They're called alpha values. Some studies accept an alpha of 0.1. Some accept an alpha of 0.01. All right? It's just the idea of what's the threshold for how willing are we to accept a rejection of the null by mistake? You know, how much chance are you willing to do? So in pharmacology, you might want to be a little more strict about how low the p-value needs to be, for example. Okay, so statistical tests spit out p-values, all right? You do a statistical test at the end of an experiment. There are multiple types of experiments that you can conduct. The most likely ones that you will conduct in conservation biology or in the field of natural resource conservation, the most likely types of studies that you're going to conduct are natural or observational experiments, or maybe manipulative experiments. You probably aren't going to have quite as many controlled studies, but you might. Controlled studies tend to be conducted in the lab or in a very, very controlled system, and they involve a group that you consider the normal group. So if you're trying to determine, say, how are fish affected by rising lead levels or rising nitrogen levels in water, you could take a fish, take some water from the normal situation, and have the fish be in that bucket and say that's the normal situation, that's our control group, okay? Then you have a bunch of other buckets that have different rates of nitrogen added to them, and you put fish in those buckets, and you compare them to the control group. And you say, oh, well, these fish did more poorly. These fish behaved differently, they got sick, all right? It seems like they can tolerate this much, okay? These fish were not different than the control group. Observational studies are when you go out and you observe natural variation in the environment. So you're trying to figure out how much fragmentation is going to affect the health of a forest, of an ecosystem type. Well, you go out to an area that has that ecosystem type, you measure fragmentation, and then you measure something else, and you say, oh, this habitat has this degree of fragmentation, and disease rates were this high, or inbreeding depression amongst the animals was this, resulted in this number of a reduction in viable offspring, okay? So these are observational, you're not manipulating anything. In a manipulative experiment, you manipulate something. They happen sometimes in ecology. You do a prescribed burn. You reintroduce a species, all right, that has gone extinct from the area or has been extirpated from the area, all right? You're manipulating something. Blind, double-blind experiments, that depends on, does the researcher know which group is which? Sometimes it's unavoidable. Let's say you're doing prescribed burns and you're seeing the effect on the plant communities. You are not going to be able to avoid knowing which group was the experimental group. Yes?
Is there a fundamental difference between controlled and manipulative, or is it like a square and a rectangle?
Controlled studies, not every controlled study needs to be a manipulative study. The idea here, and thank you for clarifying because it is tricky, right? In a controlled study, you've got one group that is considered normal, and you're comparing everything else to it. So it all comes down to how are you going to interpret the experimental results. So you can have a manipulative experiment where it's pretty clear, like your control group, let's say you're looking at bacterial growth, and you want to see if an antibiotic works. You put one disc of water on there and one disc with the antibiotic on there, and the control disc is the water. That shows that the disc doesn't affect the growth, right? So that's really straightforward. But in nature, it can be more complicated, where you're like, well, this is the natural system and the natural undisturbed setting, so we are going to call that our control group. It's our control, you see, but it's still an observational because you're not manipulating something else. The changes already happened somewhere else. Yeah, it's it can get very frustrating, and of course, whenever you set up categories like this, there's going to be overlap examples. Yeah. Okay, let's just do one more minute. I would love to get into this all of statistics slide. Last thing we have to talk about is variables. I've been hinting at them. I think I've spoken about them before, as I keep justifying. It's a new PowerPoint. I made it from scratch. And sometimes I repeat a slide or I shuffle a slide to a place where it shouldn't have been. So my apologies, you're the test group here, the experimental group. There's no control group because it hasn't been done before. You're just treatment one, no offense. All right, variables. What's a variable? It's something we can measure. That's it, okay? Sometimes it's an objective measurement, sometimes it's a subjective measurement, but it's something we can measure, all right? The quality of the patch of turf, or the height of the plant, all right? Or the salinity of the water, something we can measure. And it is key that you can always determine the dependent and independent variable in an experimental design, okay? What is the thing that we are saying will have an impact? Salinity. What is the thing that we are going to measure to determine the impact? Plant height after a month. The independent variable gets manipulated. The dependent variable depends on the value of this variable, all right? Sometimes there will be multiple independent variables, and sometimes there's multiple dependent variables, but it just takes a couple of brief adjustments to your statistical model, and then you're good to go. Or you just do each one as a separate experiment. That's also acceptable. So next lecture, which will be on Friday morning, we're going to go through the all of statistics PowerPoint, where I'll talk about this different types of data. I'll show you how to pick statistical tests, all right? And I'll show you how to interpret statistical tests. And then you'll be cruising as a statistician. You'll probably be fine through the rest of your, stats career in labs, in eco labs. Have a wonderful day, everybody. Thank you all for making it, and I will see you again very soon. All right. Hey, please.
I wasn't able to find the slides on Canvas.
Oh.
I wasn't sure if that was just a me problem.
They should be in week 1. Let's see here. Thank you. Good to see you.
In the assignment.
Just on the page. So if you just go to the home page that it takes you to, there's a little page for each week. And so you'll see right here, there's week 1, and then the PowerPoint should be right at the bottom. And the same thing for week 3. In week 3, the PowerPoint is linked right there for weeks 3 through 4.
Interesting.
Yeah.
Okay. I'll look on my computer and see if it's on
They're not showing up on the phone now.
the homepage isn't showing up at all on my phone.
Oh, that's really...
Usually they do.
They really should. I didn't put anything complicated on the home page. It should
Yeah.
function.
Yeah, I was wondering because it's saying it's posting and
Yeah. Maybe I could find a way to post like I just don't want to make it too busy. I was gonna put a section of like, here's a link to a module that has all of the PowerPoints, but then I was gonna end up with 3 things here at the top. I don't know. It's a balancing act.
no, I
Yeah.
understand. I'll check on my computer.
Okay. Let me know if you continue having problems. You can always email me and I'll email it to you as well. Yeah, of course. Hello.
Hey, so my mom passed away like 2 weeks ago.
I'm very sorry to hear that.
And
Yeah, that's
so,
terrible. Yeah.
I've been a little frazzled. I didn't realize there was an assignment on Friday.
Oh yeah, yeah.
And I was wondering if it's closed or if I could still do that. Or
It's a discussion, so it is closed, but what I can do is I can excuse you from it. I don't have any problems with that. Let's just go to the discussions. Week 1 discussion, boom. And then I just need to go to, is there a button for me to, oh, actually, no, let me just open it up to you. That way you can respond to one of the discussion points. That makes way more sense. I'll open it up for you. What's your last name?
Han, H-A-N.
H-A-H-N. Perfect. You think you could have it done by like Thursday?
Oh, yeah.
Oh, I guess that's tomorrow. Is that
Yeah,
okay?
I could get it done like right now. I don't have a gap.
Awesome. I'll just make it available until 11:59 p.m. tomorrow. That way, in case something happens with like computer access, you're good to go. Just participate in that, and I'll probably be grading those. I'll be grading those this week, but I'll wait until like Friday.
Okay, sweet. Thank you so much.
Of course, it's my pleasure, and I'm very sorry to hear that. Yeah. Good luck. Yeah. Oh,